Question 7, thankfully some stuff that you have been taught. We've got the basic idea now of resultant force. So I've got 8.4 kilonewtons up, 7.5 kilonewtons down. What's the size and the direction of the resultant force? And we've learned just take away the opposing forces. So it's going to go up. We know that for a fact. 8.4 minus 7.5 is 0.9 up. And that's because we've got more going up than down. So a nice simple question on the higher tier. Okay, next one, it says complete the diagram to show the resultant of these two forces. And they're just trying to catch you out. We can see their vector arrows have gone bum to bum. And I've taught you bum head. We want to have these. So what am I going to do? I'm going to move this force down so that it's here. That arrow down. So that vector is going to be displaced down like that. And now this is the start. This is the end. So my resultant force is going to be the one there. So you can see what they're trying to get you to do. They're just trying to get you to make mistakes where I've got to move one of them arrows. Okay. And you can see if I'd move that one across here, it'd still give me the same answer. But yeah, I don't ever want vector arrows head to head, bum to bum. Bum head is the future. Next one, the mass of the airplane is 750 kilograms. Calculate the change in GPE. I'm not going to spend very long on this. You all did this very, very well in your previous mock. But what you can notice is how important KE and GPE are. They're on both paper 1 and paper 2. Be damn good at these. So GP equals 750, no unit change, it's in kilograms, times gravity, tells me the value of 10, don't even need to remember it. And it gives me that in meters, no 1.3 kilometers or anything tricky. Multiply all of that cat together, and we get that. Done. Next part. The airplane is powered by an engine that burns fuel. The fuel supplies 6,500 kilojoules of energy. And I'm just going to have a check. Oh, this is in kilowatts, so I don't need to change it. So that part down there is in kilowatts. I'm pretty happy with that. But every minute, well, I'm going to have to change that to 60 seconds. And I think this is going to make sense now. So we've learned that efficient, useful tools, and this was done pretty well on your mock, actually. The stuff that has been taught a number of times, you're doing well on. It's just the stuff that you haven't been taught, and that ain't your fault. Here we go then. So calculate the power output. So the first part is, well, the basic part for this is I need to work out the useful output or the total output. So I need to work that out. And then once I've got this amount of energy, I can then put that into the PET formula to work out the power. So it's a tricky question. It's a multi-step, higher tier question, but I think you'd have done pretty well on this. So the output, this one here, equals efficiency times the input. So I'm just going to use the 0.7 times 6,500. I've now worked out my output. I am not going to change it because that's in kilojoules and I want it in kilowatts. But what I do have to do now is we know, well, power equals energy divided by time, but I don't want it in minutes, I want it in seconds. So 4,550 divided by my 60 seconds, and I've got my power. All right, and there's 76 kilowatts. Done. Next part, explain why the efficiency of the engine is less than 100%. As we currently know, and the laws of physics state, nothing can have an efficiency of 100% or greater. Otherwise, we have some sort of eternal machine. So it is a proven fact that the output must be less than the input. And that's because we will always get some energy will be wasted or dissipated into the surroundings. So whatever machine, whatever engine we have, there will be some wasted energy as thermal energy that will go into the surroundings. And that's that one done.